Hi everyone, this is part two of properties and materials. Um, Hopefully you've seen part one with regards to the interpretations of what those properties are. What this is going to be about is a bit of a giveaway, is the word concrete. And I'm going to look at various aspects of concrete as properties of material. So what kind of considerations are involved when considering a material for its purpose, how it's going to perform, and the various aspects that, or what should we say, the various options and the mitigation in using these materials in certain circumstances. Currently, my laptop is whirring away, as you probably will be able to hear it, and it's actually converting the part one video ready to upload to YouTube. So sorry about the whirring in the background, but I can't wait for that to finish. I need to carry on. And so let's do that. Let's carry on. Just remember that you can see here I say fitness for purpose. So that's a category. That's one of the considerations. How fit for purpose is the material. Now, as I said, I'm looking at concrete, but again, as a reminder, you should be looking at steel, timber, brick as a minimum. So how do they perform with fitness for purpose? What considerations? Because obviously you've got your exam and your project coming. You will need to know a lot more than just about concrete. And obviously I can't teach you all of this on every single construction material because this is a 2-year course and not a 5-year course. Okay. So concrete ingredients, just like it says on the left, they're proportions. So we've got something called a prescribed mix and a design mix. There's lots of others as well. A prescribed mix is effectively where I ring up a ready mix contractor and say, I want the following ratio for my concrete. That's my prescription. I'm prescribing that. Whereas a design mix is something that conforms with EN codes, British standards, and is designed mixed by the company, the ready mix company, offering specific types of concrete with specific types of mix or a mix of ingredients. Now, we also look at something called precast. So we got in situ poured, which is where we pour wet concrete on site as it arrives. And then we got precast products, of which we're going to look at as well, and the advantages of that and disadvantages, I may add. So we're looking at structural concrete. These are the types of concrete that you would typically use around a structure. So we've got the structural concrete, which of course is the real big bad boy concrete beams and columns and slabs for foundations. This is the heavy duty structural concrete, typically a minimum C35 or a C50. Now the C is a classification for concrete, so C is concrete, and 35 would be 35 newtons per millimetre squared. So 35 newtons for every square millimetre. Okay. Then we got the C50, which is far stronger, far tougher. Typically the college would be built on C50, hospitals, bridges, typical infrastructure. There's also architectural concrete, which is effectively concrete that potentially has a purpose. It generally does. It has a purpose in terms of, in structural sense, it's holding something up or retaining something, for instance. But it also looks good. Okay, so it's serving two purposes. Then we've got pre-stressed concrete, which I covered in part one, about the reinforcement bar inside being put under stress, under tension before the concrete is poured and allowed to cure and go off over the 28-day period. And then mass concrete, well, we're talking about mass pours for retaining walls and foundations. You get the idea, big infrastructure projects and elements of those projects. So as I said before, C35 grade, so this form of ready-mix concrete is usually specified at the design stage. So the calculations for beam, structural, shear, everything, all the forces that we need to take account of and then work out is C35 is effectively an off-the-shelf product. So you pick up the phone and order C35 from any concrete company, and it will be the same on every single one because it has to conform to a British standard. So mixes are measured in grades, which are calculated in newtons per square millimetre, as I said. An example, C25, C30, C35, C50, and you get the idea. C35, mostly for industrial floors, reinforced foundations, piling and underpinning. So very heavy structures, very heavy duty type performance. On the left hand side here we can see pre-stressed concrete, and if you remember, let's go back one, and if you remember what I said in my drawing in part one, where you can see the reinforcement steel bars. They're hardly bars, they're about 5mm, 6mm in diameter, and you can see that they're connecting all the way through, and then the wires are put through under tension. They're pulled in, so the concrete's poured in wet like that, and then a tension will be put onto these wires, pulled in an outwards direction, obviously under tension, and then that's kept under tension until the concrete has gone off, cured completely, and then let's say these are then cut off, so that it cuts off flush with the ends of the concrete beams, and they become lintels or a multitude of different elements of a project. And here we can see obviously a very, very big structure. Looks like a motorway deck. That's precast, so you can see the rebars inside here, ready to be connected to the next. You can see a few there to be spliced into the next section. Okay, this is post tension, and this is something that again I looked at in the previous recording. You can see that this is where, now I've done a lot of this on motorways, it's what we call steel fixing. So you can see the rebars, the steel rebars like that, and they're all connected in mesh on what we call beds and mats, and they're all tied together usually with a stainless steel wire. And then we can see that these are going to be obviously columns that are going to be projecting from, this is a main slab, obviously this is a foundation main slab. With these slabs, with these reinforcement bars here, effectively what would happen is that more once this is all poured, there'll be shuttering or a post-form system that's put around these columns, in other words like a mould, and then the mould is put around here, and then concrete is poured in. But prior to that, not prior to that, but concrete will probably be poured up to around about here, and then you'll just see these bars sticking out at the top. I think minimum 500mm or 50cm would be sticking out, because that's the requirement for what we call splicing. So to continue the column up for the next lift, the next floor, the reinforcement bar would be tied to these at least half a metre, 500mm splice, and then the next deck would be poured, and that's how we do continuous column forming. And then on this example here, this is what we call post-tension concrete. So this is, as the concrete is actually poured in situ like this, where all the steel sleeves and cables, they're all just lying on the floor like this all week, whereas opposed to this is all pre-stressed. This is all, this is what you see is what you get there. They're all fixed in situ. There's no post-tensioning involved with this. This wouldn't be as strong as the post tension, and you can see in the environmental sense and cost sense, this is going to be way heavier in terms of cost and use of materials, because you can see clearly how much steel is involved with that one. Whereas this one, there's far less, but this is, the tension is put after the concrete is poured, and the tension is increased week by week, and until a point where it's got maximum tension on it, and then the tendons are cut off at the end of the slabs, and this provides opportunities for far less steel to be used, and it's far stronger as well when you're looking at that type of construction. So here's a question: how would you rate concrete then? We've all seen concrete. We've all walked on it, we've leant against it. Some of me, you've fallen on it. It's quite hard stuff. Usually looks great. But what would you say in terms of its visual appearance? Would you say concrete is beautiful or ugly? So, here is a very, very nice floor. Now, this has lots of advantages. This is a highly polished concrete floor. And the advantage with this is that you can put lots of different types of finishes into the concrete to give this like stone speckle finish, and then it's finished off with various resins and lacquers and highly polished. Remember about thermal mass, don't forget concrete is a thermal mass where it absorbs heat and it releases it throughout the night when it's cooler, so it maintains house temperature more evenly and longer. And then this is going to be very, very hard wearing, very durable. I don't know if any of you have come across concrete kitchen countertops. Again, they're extremely expensive and beautifully finished, but it's concrete. So, you know, mostly kitchens have a laminate or a solid wood. Solid wood can be very expensive, but concrete is next level. It's the same as like marble and granite worktops. It's up there the same as well. So there's lots of advantages to actually manipulating the look of the concrete. This is acid stained concrete. Again, you can see that's a beautiful finish, really, really nice, extremely hard wear, and it's got the thermal mass factor about it. It's obviously, so it's dried off level. It can easily be maintained, and it's very desirable, very aesthetically desirable. And then we've got an external one. This is called stamping. So we create like molds. So we've got timber molds or metal molds around the step, and then we pour the concrete in, and then we have these large pattern stencils that are just literally poked into the concrete, stamped into the concrete, which gives you all of this, all of the grain that you see inside of here. And then of course you're using different coloured type of concrete to give the contrast between the two. But again, a very durable looking driveway. Unlike tarmac, where you're going to get various bits of vegetation growing, you're going to get oxidization of the tarmac as soon as it's laid, so therefore eventually it's going to break down through electromagnetic radiation, e.g. Sunlight. It starts to break it down, starts to fade it, and starts to create what's called alligator effect, crocodiling, and starts to break up with something else called freeze thaw, which we'll come on to a little bit later in this presentation. So you can see there's some really nice examples of concrete. Don't forget, you should be looking at steel, concrete, steel, timber and brick, and I'm sure you'll be coming across some very beautiful examples of how they can be used aesthetically as well. So you've got reactive stain acid paints, a little bit like the acid staining that we just seen on this example. Okay, so it's just another, it's very bespoke, that one, very, very but I mean very expensive to lay as well. So what I want you to do ordinarily in class, I would say to you, you've got 15 minutes to investigate steel used with a concrete structure, in particular focus on the fitness for purpose as a structural foundation. So we spoke about the rebar, the post-tension, pre-tension, and then what about the examples of grades? So what kind of grades? So concrete out was a C30, C35, C50. What about steel? What grades of steel are there in terms of examples? So give yourself 15 minutes, pause this video, and go and take a look and see what you can find. Okay. Now, when it comes to cost on projects, this is a view that's seldom seen. This is about concrete itself, just the cost of concrete. And sometimes the budget of the total cost of a project, they're re-specified, because during the planning stages and design stages, materials go up, certain regulations have changed, meaning some materials have to be altered at cost, and therefore that can have a big impact. And certainly when you're doing without a foundation, you haven't got a building. And so this is one of the critical ones where it's pretty much never compromised, because if you take the college, for instance, that college has to stand up on a foundation that's capable of upholding it. So you need a minimum specification for it. You can't alter that. It has to be what it is through the architect's specifications. Okay. So if we look at it itself, the concrete materials, let's suppose this is a £1 million foundation project. So £218,000 of that would be the materials itself, which is that leaves about 80% for everything else. So it's not actually the greatest cost there. You've got the concrete labour to obviously for people to install the concrete, whether it's poured in situ or it's prefabricated. Again, poured in situ is where it's a liquid form that you can manipulate and place into moulds and spread and tamper and polish and screed. There's all sorts of things you can do when it's a live material. Obviously, there's a certain amount of time that you have to work with. It's very labour intensive, whereas prefabricated would be you just need a crane and a few people to just bolt it into place and then finish the joints, the seals. But obviously, if the measurements are wrong and the panels don't fit, you're in big trouble. But the pre-stressed concrete panels, they're very expensive as well, because all the labour has been taken out. So that's what you're paying for. You're paying for speed rather than finesse. And on certain projects like the project that you've got, which is your development in the middle of that town centre, where you've got retail one side and domestic on the other side, and you get the child's playground. You've got nowhere to store materials, nowhere to pump large amounts of concrete. So you'll be using typically a just-in-time, JIT, just-in-time delivery, which is very tight schedules where concrete panels would just arrive and within an hour they've been lifted off by crane and placed in situ within the project and then connected up. So just-in-time delivery. Then you've got the reinforcement materials. So we're talking about the reinforcement bar, the rebar, the steel. You've got the reinforcement, the steel fixing labour for that. And then you've got the formwork materials, which is basically the panels that are fixed together, of which the steel is going to be placed into in the centre, and then the concrete is going to be poured in afterwards. And after a few days, the formwork is struck off. So you strike the formwork. It's a term for just literally peeling the formwork back off the concrete, and in order for the curing process to speed up and continue to full hardness. And then you've got the formwork labour, so 46.7, that's huge. So, but then if you don't have the formwork, if you don't have the mould to whatever you're trying to produce, then you can't pour concrete. It's as simple as that. So there's some interesting figures there when you take a look at, if you take a look at a foundation, it's not just about the concrete. In fact, the concrete is only 20% of the whole thing. Most of it's actually labour. Now, resistance to degradation. Remember, you are looking at timber, steel and brick as well. Okay, so what we're going to look at is how do we ensure that the selection materials are appropriate and fit for purpose in the first place, and to prevent such things as what's happening in that picture there, which is a result of acid rain, delamination, spalling, effectively it's a concrete cancer. Okay, and obviously once those rebars are exposed, you're in serious danger of the structure deteriorating very, very quickly as a result of that. The steel bars are there for a reason. If they start to rust and start to deteriorate, then obviously that structure is getting weaker and weaker. And guess what? It's happening at the base of that wall or that slab. So, you know, it wouldn't be the worst risk at all if it was at the very top. But certainly at the bottom, it's bearing all the load. So that's why this is incredibly important that we understand this better. Now, when we actually use materials such as stone, cement, sand. These materials are often imported from other countries, and unless these materials conform to British Standard BS or Euro Norm Codes EN, then the quality is compromised. And as a result of the quality being compromised, along with that material comes certain chemicals that are going to attack the concrete from within. So if we look at a physical, this is where the sulfate containing water enters so it's water containing sulfate, enters the surface of the concrete, it crystallizes and expands, disrupting the hardened concrete. So you know that fluids expand when they're frozen. It's the same thing. And it's the same thing when we talk about freeze thaw, of which we'll cover shortly. We've got the chemical attack, where the sulfate salts react with the Portland cement paste, which is a cement powder, and it causes it to dissolve, soften and erode. And then we've got the internal sulfate attack, and that occurs mainly in precast concrete and has been attributed to high curing temperatures or cement chemistry. Now, one thing to understand about concrete is that when you apply water to the cement powder, to the concrete, the dry mix, you get something called an exothermic reaction. Exothermic. I think the thermic gives you a clue about what I'm talking about. Effectively, if you was to touch concrete after several hours of it starting to go off, starting to cure, it's going to be very, very hot, very hot. And a little bit later on we talk about the health and safety of concrete, where you've got to wear gloves, glasses and boots, because if this gets onto your skin and it allows to penetrate the skin, it burns like an acid. And the unusual thing about concrete is if it gets into an open wound or it breaks through the skin, it keeps burning for days. It goes deeper and deeper and deeper. It really is a vicious material if it's not handled correctly. And there's various chemicals in that material. Certainly we get certain additives, pulverized ash, for instance, aluminates, sulfates, all sorts of chemicals, retardants, plasticizers, all different chemicals to make the concrete react in different ways to certain situations. Now, freeze thaw is the main problem, and effectively what that is, you can see the image on the right. So when you're driving down a road and you can see that the road, there's potholes and there's cracks in the road, and then you got what's called concrete heave, where you see big humps forming in the middle of the road. This is what the cause is. Effectively what happens is you need, when you pour concrete, you need to vibrate it with these vibrating pokers. So you'll see the guys standing there dipping these long pokers into the concrete, and they're trying to vibrate all the air pockets out. And if it's poorly done, when air pockets are exposed to rain, to water, of course, especially at this time of the year, well, in winter time, the water freezes and expands, and then it starts to break down the concrete around it. Then it thaws, but now you've got a slightly bigger hole than the night before. And this process continues and continues, and then it starts to actually break up the concrete. It actually starts to crack it up, and of course, as it starts to crack, it allows more water in, more freezing, more cracking, and then we've got some unraveling of the road surface or the surface of the walls of a bridge or a tunnel. So it's very important that we make sure that we get these pockets out. There is something else called air entrained concrete, and effectively what this is where we want to put air pockets into the concrete. So it's a bit weird that way. We're trying to vibrate it all out to get that freeze thaw issue under control. But with air entrained concrete, typically that could be used as an access road to a farm where no connecting drainage is available, and that the air pockets are big enough, they're deliberate and they're big enough to hold water and drain away. So it's quite a good strategy where it's allowed to expand in these pockets and it's not going to cause too much issue. So that's when we use it to our advantage. Resistance in terms of alkali silica, So this is a reaction that forms an expansive gel that causes concrete to crack. So think of freeze thaw, but instead of the freeze scenario, this is an expansive gel contained from silica, which is a natural product in concrete. So when high alkali cements and silica bearing aggregate are exposed to humid conditions, a reaction occurs that creates the gel. And then when that's exposed to water, it can expand and fracture the aggregates and cement, just like the freeze thaw. Okay, but it's the same. You can see there, it's the same outcome. It's the delamination or dilapidation of the concrete itself. It's starting to break down. And then we've got carbonation, concrete carbonation. So again, it's very similar. It's open to carbon, silica, freeze thaw, everything. This is mostly about acid rain eating away, like a concrete cancer eating away at the concrete itself. There's various things we can do to do that, which is in the first place we can look at half cell potential testing, where we look at the positive and negative electric flow of current through those reinforcement bars. And what we're trying to do, we put cathodes or we put anodes. We drill little holes into the surface of the we drill holes and put cathodes into the wall, and then we connect little wires up to the rebar itself, and then we put a small current through those rebars. And what we do, we put cathodes at various points connecting the wires, where it draws the negative neutrons towards that, so it takes the corrosion away to a managed point. So it's very strategic and very precise, but sometimes we can't just demolish a bridge and rebuild one. Sometimes we just have to maintain it as best we can so it still stays fit for purpose. So the carbonation itself, it depends on the following factors. So the presence of pore water, so how much water is getting within the structure itself. It depends on the grade of the concrete and how permeable, so how porous, how much water is actually allowing to soak in. How much unprotected concrete there is. The depth of cover, and effectively what that is in terms of cover is that typically you would have 50 mil cover between the formwork and the steel frame. So you put the reinforcement bar together in, say, a cage or inside your formwork. So the formwork is the mould. Then you put the steel inside. Generally on big projects like motorway bridges, which I've worked on, you form the steel work first, and then you put the formwork around, and you've got these little concrete blocks which are 50 mil in length and 35 mil in width. And when you're doing the steel fixing, it'll say on the architect's prescription whether it's 35 or whether it's 50 mil cover. And effectively, if it's 50 mil, you tie wire through the blocks onto the outside of the steel frame, the steel mesh that you put together. Excuse me. And then the formwork is built around that tightly up to these blocks. In other words, there will be 50 mil of pure concrete between the outside and the steel reinforcement bar when it's all cured and when it's all one big concrete block. And that's what they mean by depth of cover. And then the time, we're talking about the curing time. Okay, so how quickly, it could be a problem with how quickly it cures or how quickly it doesn't cure, could be another factor. Pores in the concrete are dry, then CO2 remains in gaseous form and does not react with hydrated lime, and carbonation cannot take place. So what happens is when you make concrete, it releases carbon, CO2 emissions. That's what it does. Okay, so it's one of the worst culprits on the planet for producing CO2 is concrete materials, and particularly concrete itself. The higher the grade of the concrete, the slower the rate of carbonation. So big infrastructure buildings that's using C50, for instance, it's a much slower carbonation. And of course, when we talk about the drying time, depends on how much carbonation takes place and how much reaction has took place with hydrated lime. And definitely the concrete which are protected are less prone to carbonation. So when it's curing, it's usually there's damp sheets, Hessian sheets that are placed over the concrete to control the curing process, the exothermic reaction. And then there could be, if it's in direct beating sun, you're going to have to do something about it, you know. And then you've got the long-term cover. So is there a protective surface on the concrete as well that's stopping certain elements of certainly moisture, vapor, acid rain from penetrating it? Installation, ease of use. So this is live concrete being poured, and then you can see, of course, there's the regular steel. Your man standing on it. It's something I've done a lot of this, and then it's poured in place, and then the pokers are plonked in between all these squares, all these steels, and then obviously vibrated out. The air pockets are vibrated out. So it's very flexible form of installation. So environmental implications. So we have to take embedded energy into account. So you have 10 minutes to highlight the main environmental factors surrounding the production of concrete. So can you just take a look for about 10 minutes about what, if you was to Google what environmental considerations has concrete, okay? You've got the CO2 emissions, how much CO2 is emitted. And you'd be surprised, it's actually ton for ton. So a ton of concrete that's curing on what we call Portland cement, it will release a ton of CO2. That's a huge amount. That's absolutely huge. Okay, so there's things like that. And then you've got the embedded energy and the embedded carbon. What we mean by that is how much energy is used in the extraction of the raw material from the quarry, and then transported through to the manufacture of the Portland cement. We're going to look a little bit later on about this as well. I think that's in part 3, if memory serves me right. In terms of the environmental implications, I want you to look at cradle to grave design. And effectively what that means is the cradle is the inception of the project. So the extraction of the raw materials is the cradle. And then the grave is actually when the building has fulfilled its life cycle. So it's been used for approximately 65 years, and then it's brought down. And what do? So we need to look at the grave situation. So what happens then? So we need to design and build much more sustainably with the grave in mind. So how recyclable, how reusable, how reclaimable are the materials? And what happens with concrete? What happens to the big massive concrete foundations that are no longer needed? So have a look at that and see what you find. What do we actually do with it? This picture here is interests me or intrigues me. We'll come back to that in a second. This fact on the left here, since the 1990s, the UK cement industry has reduced its energy used to make Portland cement by almost 25%. Okay, and in turn, CO2 emissions have been lowered by over 3 million tonnes. But that doesn't really mean anything unless you know the total amount of tonnes that are being produced. So that's a real generalised figure there is. We can't really benchmark it against anything. But this one on the right, it says on there underneath the phone number, low carbon cement. Well, what does that actually mean? It's a bit of it's something that you'd have to go onto the website and take a look. I mean, it could say that we're using biofuel in our lorries to transport a material that releases 1 tonne of CO2 emissions for every tonne that is made. So effectively, a cubic metre of concrete is a tonne. So them lorries there, if they're carrying 30 cubic metres, that's 30 tonnes of CO2 emissions. So I think it's a bit cheeky myself to say that's low carbon cement. I think it's a bit of a statement they need to substantiate and actually be clear on what they actually mean by that. We spoke about the high thermal mass with concrete when we were looking at the aesthetics and the advantages of that. So high thermal mass, obviously the concrete is trapping the heat of the day into the concrete and then releasing it at night time, which is a good way of maintaining consistent temperatures throughout the day and night. And we've got the RAC, the recycled aggregate concrete. So this is a bit of a clue as to one of the tasks I've asked you to do into looking at the environmental implications. And it's certainly when we go cradle to grave, what happens to the concrete and the foundation? Well, there's a recycling potential, but what exactly do we mean by that? And what is it used for? How do we recycle concrete? And where can we see examples of the concrete once it's been recycled? What do they do with it? So the advantages and disadvantages. Okay, so the advantages of don't forget this is all about recycling. Okay, so it reduces the amount of raw aggregates needed for a project. So we're drastically eliminating the need for raw energy, embedded carbon. We're releasing far less CO2 as a result of it. While being crushed into smaller particles, a large amount of carbon dioxide is absorbed, and this reduces the amount of CO2 within the atmosphere. Research studies have shown a significant reduction in construction costs, and that's obvious if RAC is used. It conserves landfill space, so we're no longer sending concrete foundations, beams, columns, structures to the landfill because we use them now. It creates more employment opportunities within the RAC industry. And the disadvantages, so it's downgrading of quality of concrete. So obviously if you've got a concrete slab that's intact, that's far stronger than when you break it all up into little bits. Effectively, that's what that means. There's an increase in water absorption capacity ranging from 3 to 9%. So because you broke it up and you've created more porous surfaces, therefore there's the increase in potential for absorption. It's got a decrease in compressive strength of concrete to 10 to 30%. As I've just said, when you break it all up from a big slab, it's obviously far weaker in its consummate parts, smaller parts. Reduces workability of concrete. So when we're installing concrete fresh, when it's wet, that's got huge workability. And obviously once it's already gone off and broken up into hard little bits, obviously there's not much workability there. There are a lack of specifications and guidelines, so it's very difficult to determine the strength of the concrete when it's all broken up like that. And less durability of RAC. So a few papers have shown apparently an improvement in the durability by mixing it with special materials like fly ash. Fly ash is a byproduct of the coal industry, where they burn coal in fuel stations to produce electricity, and that's what the fly ash is. So they're using that. Interestingly, they used they actually, there's a power station called Draxler. I think it's Draxler. Oh no, it's just called Drax. Honestly, go to YouTube and look at the video on Drax. It's an absolute monster of a place, but it's brilliant. I mean, the amount of figures that's involved is incredible. The amount of coal going in there, the amount of electricity that's being used. But what they do is they capture the carbon in these carbon banks. Very specific process, and what they do with that carbon, they turn it into what's called gypsum. They mix it with gypsum, and we create plasterboards. So the byproduct of the coal industry, the power station industry, with fly ash and carbon CO2 emissions, are actually captured and used as a construction material, which we've got in every single house, and it's held inert. In other words, it's inertia, so it's not a live material, it's just trapped and captured. Like asbestos, I think you all know asbestos is very, very dangerous, only if you're working with it, if you're cutting it or you're moving it, when the particles start moving around in the air. Asbestos, when it's just sat there in like a form, like a panel or a roof tile, it's not dangerous at all, because it's captured, it's inert. It's no longer a live element until, as I say, you start breaking up the material itself, and then it becomes the airborne particles, and that's when it starts to become a real issue. So I did mention earlier about the gloves, the goggles, protective boots, Wellingtons for when you're working with concrete. There's a lot of chemicals involved. You've got your cement burn. If you was to get it in your eyes, it's not going to be good. It really isn't. It's a really, really difficult material to work with if you don't observe the safety that comes with concrete. It looks very innocent. It can be really, really dangerous, very dangerous. And then you've got the compatibility, so how compatible are materials with, so ordinarily steel does not mix with water, and concrete is not the best with water because of the porosity factor. However, certain plasticizers and additives and retardants within concrete mixes are designed to prevent adverse reactions from mixing with other materials such as water. And the same goes for steel. If we galvanize the steel, it becomes utterly water resistant, so we can put it in water. We've got concrete mixes that we can pour live concrete on a riverbed or on a seabed, and it will go hard because it doesn't need air to actually oxygenate it and cause that rapid exothermic reaction. And that's how we effectively build oil rigs in the middle of nowhere in the sea. So the last thing I want you to do is investigate remedial techniques for the maintenance of a concrete motorway bridge. And in doing that, I want you to look at these aspects on the right. So corrosion. So what type of techniques can we use to reverse corrosion or protect the bridge against corrosion? What kind of techniques are available? Spalling concrete, what would we do there? How can we manage acid rain on a bridge? And what about the exposure of that reinforcement bar? As we've seen pictures of that where we have the spalling and delamination. And remember, you really need to look at these to understand how remedial techniques are formed to protect structures from deteriorating. And steel, timber and brick, and they're no exception. All of those materials also delaminate. They also fail under load and fail in performance if they're not remedially maintained. So don't just look at the concrete in terms of corrosion, spalling, acid, exposure, reinforcement bar. Look at the techniques for maintenance of steel on a bridge. What about a timber bridge? What about brick viaducts and brick bridges? How many times a week do you pass under a bridge, a railway bridge that's built of brick? And what about the dilapidation of that brickwork? It goes on all the materials. So look into it. You need to understand that once we use a material, we've decided to use a material and allocate this to a particular project, we also have to understand how we're going to maintain it, how accessible it is to maintain it, the cost of maintaining that over the life cycle of the structure, and what can we put in place in the first instance in terms of protective coatings, if any. So these are all things that you need to consider in terms of the materials and some of the stuff that can degrade them. So that's the end of part 2, and in part 3 we're going to look more on the sustainability side of things in terms of embedded energy.